All right. So, moving into some calculus. If you want to think about it, we're kind of starting to dip our toes into the water, and then eventually here, this next week, we'll actually jump all the way in. But for right now, we're just kind of dipping our toes with a little bit of calculus, kind of building those foundation, those building blocks to get us where we need to be. So, starting with the kickoff here, what are those two basic problems of calculus? Well, the two are the tangent line problem and the area problem. So, tangent line problem, finding that instant slope, and then like area would be area underneath the curve. Are there two main basic problems of calculus that everything kind of builds from there. But if we looked at, say, this function out here, f of x equals x to the third minus 1 over x minus 1. And notice how x can't equal 1. Well, what if we want to find what is the value when we are at 1? Obviously, we can't just put the number in and find out what that is with the equation of how it is. So how do we find that value? Well, we find it by determining its limit. So determining the limit is pretty much what is our y value. So what are we getting out of this graph at a certain x? So here we can't see what it is at that point, but we can see what is the graph going towards, and we can get close enough to say, you know what, this is what the value would be if it did exist. One of those ways is by doing a table here. So if we looked at, and they're going to write it like this. So LIM stands for limit. So the limit as our x approaches 1. So as we get close to 1 on the x, what is our y value, our function, doing on our graph? Now, using the table, what we're going to do is we're going to keep picking values that are closer and closer to that value. And we're going to be able to kind of see what the pattern is going on, where that trend is going. Now, looking here, we're getting closer and closer to 3 on both sides. So that's what that limit's going to equal, is 3 in this case. So one of those ways is we can use that table. This is where we can use our graphing calculators and put our equation in, and then put in these values in your table on the graphing calculator. Or you can set up your own table and put in the values individually and do all that. But a table is one way we can do it. You can see what the values, what those y values are doing as we get closer and closer to that x. We can also use a graph to find that limit as well. And I'm going to show that graph with this next part as to whether the limit exists here. Find out what that limit is. So if we graph this out, we're dealing with a piecewise function here. So what it's saying is when x is not 2, we're going to be 1. However, when we are at 2 on the x, we're going to have 0 for our y value. So as it's going through, if we have 1, 2 here, say this is going to be that spot, 1, 2 going up. Always we're going to be at 1. So the rest of the time, we're going to be cutting through here with our graph. So it's going to look like this. So in this case, that point is going to be at 0 for our y. So it'll exist and be at this point. But the limit, as far as it goes, as we approach that point, our y values are actually up here at 1. So looking at this graph, we can go, okay, as we get closer to there, as we get closer to our point, okay, we're going to our 1 here. So the limit as x would approach 2 of f of x, so we're going to leave it as that since it's a piecewise, is going to be equal to 1 in this case. So limit, think of it as where is our y going as we get closer to that particular x. So what value will we get out of this graph? Now, there's going to be certain cases where the limit will not exist. So this first case, this is going to be one of the cases here. We're going to look at this example of the limit as x approaches 0 of the absolute value of x over x. So obviously we can't just put 0 in and find out what that y value is going to be, because then we get a 0 on the bottom, and that's bad. We can't divide by 0. It's going to be undefined. So, well, what value would we get? Well, if we just had x over x, that's going to go to be 1. However, with ours, we have an absolute value. So we're going to look at when x is greater than 0. So when x is positive, what's it going to be? And when x is less than 0, when x is negative, what's going to happen? So on this case, absolute value, we're always going to have positive on top. And being our x is positive, we'll have positive on the bottom. Positive or positive, we're going to get a 1 in this case. Where it's going to be different is down here. So when x is less than 1, so when x is negative, the absolute value on top is going to keep that positive. The bottom is going to be a negative. Positive over negative makes this a negative 1. Because these are going to not the same thing, the limit's not going to exist. So both sides of the limit have to equal. So if they don't equal, they cannot be a limit. So each side has to be coming to the same value. If they're going to different values, it does not exist. Now, the next part of this we're going to kind of get into involves, here's the Greek letter delta. I know delta is also a triangle. I need to look into as to why delta is a triangle and this S-looking shape, but I have not got it done yet. So that's something that's coming up. But the Greek letter delta S, or kind of looks like a squiggly S, is what we're going to use here. So if delta is a positive number, then the x value satisfying the inequality 0, the absolute value of x is less than delta. The values, absolute value of x over x can be classified as negative delta to 0 and 0 to delta. Well, what that's really saying is this delta, and I'm off the video, sorry. What this is really saying is this. Delta is going to be how far off of our x that we can be and still find the limit. So how close do we need to be to the x value we're approaching before we're going to get a number small enough that we can go, you know what, this has to be the limit. We're getting closer and closer to our y value. This is what it has to be. So there's going to be on both sides of that. So from no difference up to the positive amount over, and then, or the positive delta, that amount over, and then from nothing to the or negative delta to the left side, we're going to have a variance there. So we're going to get more into this in a little bit. But for now, another case in which the limit won't exist is when we have something like this. So if we're 1 over x squared, obviously if we go to 0, that's not going to work out well because we can't divide by 0 again. So if we do just a tenth off for our delta, so if we're within a tenth of what x we're trying to get to, what value would we get? Well, if we put a tenth in for our x here, 1/10 squared would be 1/100th. So when we flip this, because we'd be 1 over 1/100th, is going to end up being 100. So now if we do 1/1000th, when we square that, we're going to be 1 over 1/1,000,000th. So when we flip it, we get 1 million. So as you see, the closer we get to our x, so if we have less and less of a difference, our numbers are going to start going up by a lot. This is going to end up being one of those where as we get closer to 0, we curve up and go to infinity if we're looking at our graph. So if it goes up here to infinity or to negative infinity, the limit won't exist. So infinite limits do not exist. So if you think about it, the limit has to go to a specific number that we can say, hey, this number right here is the limit. Here it's unbounded. We don't know what number it's going to. Now, we assume it's going to infinity. It may level off somewhere. We don't know. Either way, it's going up so fast, we can't tell what it's exactly going to. So if we can't tell exactly, the limit won't exist. It has to be an exact number for the limit to exist. Here's going to be our last case. So if we would pull up the graph, and let's see, I got a graphic calculator here. If we would pull up the graph of the limit as sine approaches 1 over infinity, right in the middle is going to do something like this. So it's going to start bouncing back and forth between -1 and 1, which what sine does, so fast that we don't know what exactly it's going to go to at that point of 0. Number one, we can't put 0 in there because that'd be undefined on the bottom. But it's going to bounce back and forth so fast, we can't say what the number is. So it kind of goes back to the last one. You know, if it was going up to infinity, again, we don't have an exact number it's going to. We can't say the limit exists. Same thing here. If it's bouncing back and forth, we can't tell that exact number. So we can't say the limit exists. So it's going to oscillate. So if it oscillates, limit, and I'm going to shorten it up to DNE, does not exist. So it can't oscillate, it can't go to infinity, and it can't have different limits. So that's what sums up here. So places where it cannot exist is f of x, so our graph cannot approach a different number from each side of our c, our x that we're approaching. It also cannot increase or decrease without bound as we get closer to that x. And then lastly, it can't oscillate between two numbers as x approaches c. So it can't bounce back and forth. It has to go to a specific number in order to exist. The next part about this is we're going to deal this E-looking thing, kind of a backwards 3. It's called the Greek letter epsilon. Now, we're going to use epsilon and delta in order to make the official definition of a limit. So I'll read through that here, and then I'll kind of sum this up. So let f be a function defined on an open interval containing c, except possibly at c. So that's the x we're going towards. And let L be a real number. L is going to represent our limit. So the statement, the limit as x approaches c of f of x equals L, means that for every epsilon greater than 0. So we can't have a negative epsilon, but an epsilon that's greater than 0, so positive epsilon, will exist a positive delta as well, such that if 0 is less than the absolute value of x minus c, is less than delta, then the absolute value of f of x minus L, our limit, is going to be less than epsilon. So think of it as the difference that we are away from x has to be within a certain delta. So think delta applies to x, such that our limit that we take away from our actual function that we're using is going to be less than an epsilon. So think epsilon is how close are we to our actual limit that we can say this is going to happen, and delta is going to be how close we have to be to x in order for that limit to happen. So delta ties with x, epsilon ties with y. So these are going to be the base equations that we're going to use in order to show that the limit's going to happen. So the problems you're going to have to work out will be like this. So in this case, you're going to need to find a given delta, or find a delta for a given epsilon. So they're going to give you what epsilon is. So given the limit of 2x minus 5 as x approaches 3 is 1, find the delta such that the absolute value of 2x minus 5 minus 1 is less than 0.01, wherever 0 is less than the absolute value of x minus 3, which is less than delta. So here they're setting up those equations already. This one here is, and I'm going to move this 0.01 over there. So this is that absolute value of f of x minus L is less than our epsilon. This one here is 0 is less than the absolute value of x minus c is less than our delta. So that's how they're setting these up. Now, the thing will be is we're going to solve this side out so that matches here, and that'll tell us what our epsilon and deltas need to be. So if we start off with this one here, we can put like terms together here and have the absolute value of 2x minus 6, which is less than our epsilon of 0.01, or delta. Yeah, our epsilon, sorry. So 2x minus 6 doesn't match our x minus 3 yet. Well, we can pull a common factor out. We can pull a 2 out, and then we would have x minus 3 in our absolute value, which is less than 0.01. So to solve for this, to get this equal, we're going to divide by 2 on this side, so which means this side is going to be divided by 2. So the absolute value of x minus 3 is going to be less than 0.005. So think we're going to sub this in to here for that absolute value of x is less than, or x minus 3 is less than delta. So if we know this is going to be less than this, we can sub this in. So 0.005 is our delta. So we have to be within that in order to have our limit exist. So if we pick an x within this, we're going to be within this for our limit that we can say that's going to happen. That's where that's coming from. So we're going to prove the existence of a limit now for any epsilon and any delta that's going on. So we're not given any values of either of those, but we can still set this up and find it. So remember, as x approaches whatever is our c, the parentheses here after limit is our f of x, and what we're equal to is our L. So if we set this up, our 0 is less than absolute value of x minus c, it's less than delta, and over here I'm going to set up our absolute value of f of x minus L is less than epsilon. So 0 is going to be less than or equal to the absolute value of x minus our c is 2, which is less than our delta. Here, f of x is 3x minus 2 minus our limit, which is 4. Sorry, volleyball team's getting ready. So if we simplify this down, we're going to get 3x, the minus 2, the minus 4 is going to be minus 6, is less than our epsilon. So we're going to pull out a 3 here to make this x minus 2 less than epsilon. So to get this to be where it needs to be, because we're solving to try to make it match x minus 2 in absolute value, we would divide by 3. So in that case, when we sub this in, our delta has to be whatever epsilon is divided by 3. It has to be within that. So if our epsilon is 0.1, we'd have to be 0.1 divided by 3. That close away from our x, or whatever it is. If it's 0.001, it'd be that divided by 3. All right? So, last case where this is going to happen. Well, last case that we're going to go over anyway. So again, this is our c. This is going to be our f of x. This is our limit. So when we set up our absolute value of f of x minus L, which is less than our epsilon, and our 0 is less than the absolute value of x minus c, which is less than delta, we're going to have absolute value of x squared minus 4 over here in absolute value, less than delta, epsilon, sorry. Over here we would have the absolute value of x minus 2 again, which is less than delta. So, in this case, we don't have a common factor we could pull out. So we're going to factor this. This is going to become the absolute value of x plus 2, x minus 2 within our epsilon. So we're going to split this up so that our absolute value of x plus 2 is the one absolute value times the other absolute value of x minus 2, which is still less than epsilon. Now, you might go, well, to get this to match, we're just going to divide this x plus 2 over. Well, that still leaves us a problem. We're going to have a second variable of x and our epsilon. We don't want that. We want a specific value we want in order to make this work. So if you think about it, if we take our x plus 2 in absolute value, we're going to pick an x on either side of what we're approaching. So if we think about 1 and we think about 3, 1 on either side of the two that we approach. If we put 1 in here, we would end up with 3. If we put 3 in, we're going to end up with 5. So if you think about it, all of our values are going to be less than this right here, our 5. Not all of our values are going to be less than 3. So 5 will cover whatever we're going to be dealing with, because we're going to try to get closer and closer to what x is when x is 2. What y is when x is 2, I should say, with our limit. So if we use our 5, that's going to cover anything we could possibly have. So if we're within that, when that value is 5, we're going to be good. We're going to be closer than what we need to be, which is good. The other way we could be too far. We might be about right, but this way ensures that we are good. So we're going to sub this in for our x plus 2. So we're going to have 5 absolute value of x minus 2 is less than epsilon, so we would divide by 5 to have our value. So epsilon over 5 is going to be our delta. So if we're within that epsilon over 5, we're going to be good. So that'll give us close enough to whatever our delta needs to be. So however close we need to be to y. If we pick an x that's within 1/5, if you think about it that way, of whatever epsilon is, we're going to be golden. So that's it for the lesson. Let me know if you have any other questions. Until next time, we'll talk to you later.